Good afternoon. The title of my talk today is a lake-wide acoustic survey with autonomous uncrewed vessels in the world's largest lake. I'd like to begin by thanking my co-walkers. Through their hard work, they realized what we imagine as a future for conducting lake-wide surveys of pelagic fish populations in the Great Lakes. I stand in front of you, as always, as their good-looking frontman, their Brad Pitt, if you will. But seriously, I hope you'll be impressed by what my co-authors accomplished. I sure am. By way of an outline, I'll set the stage by first talking about prior lake-wide surveys that the Great Lakes Science Center has conducted on Lake Superior. There's been 4 such surveys over time. I'll talk a little bit about Saildrone 101, or introduce you to the technology we used. I'll share the questions that we sought to answer, talk a little bit about our survey design and the processing steps we used. The bulk of the talk is going to be about results, and I'll close with IC as the take-home messages. No, one too far. Yeah. What the heck? There we go. I got to figure out the technology. Don't say anything, Mike. I'm good. So the purpose here is one of the major drivers of this work was to estimate the abundance of the ciscos in the lake after the strong recruitment event in 2022, when we measured that recruitment event based on age 1 catches in 23 and set records for all 3 species that are listed here. So many of the things we were trying to learn is what was the current status of these populations after this big population boom. We've had opportunity to conduct 4 lake-wide surveys in Lake Superior since the turn of the century. The first survey took 4 years. We divided the lake in quadrants and did a survey each year, or did a quarter of the lake each year. And then after that, we adopted what was called the 2011 survey, the Cooperative Science and Monitoring Initiative survey, which is shown the design in the map in the right-hand corner. This has 56 stations. It's spatially balanced. It's depth stratified. It's really quite a marvelous design. At each of those 56 stations, we collect 2.5 to 3 kilometers of acoustic data and 1 to 2 midwater trawls, depending on how much time we have. It turns out that this is funded by reimbursable dollars through the GLRI. So the frequency of these surveys is about every 5 years. And that's a long time to wait for updated information. I think it's a really nice design because it lets it speak about the whole lake, but managers I'm come to appreciate like to have estimates at smaller spatial scales like jurisdictions. The results of the 4 surveys are in the bottom right-hand panel. The populations of ciscos had been in decline because there had been several years of really poor recruitment. So from the first survey to the 3rd survey, we saw fewer and fewer ciscos, and then that all changed in 2022 when we caught in huge numbers that 2022 year class as age zeros. A little background on Saildrone. What happens is USGS sets up a contract with this California-based company. Its drones are also called Saildrone. It's what you call an uncrewed surface vessel, or USV. You'll see me use that acronym throughout. It's green energy powered by wind and solar. It has echosounder as a payload and as a little miniature transducer that's mounted on the keel. We load up transects for it to run into a web portal, but those can be adjusted depending on when the wind conditions. The Saildrones are run or supervised by Saildrone 24/7. And the agency, again, paying the contract, can alter those transects every night within reason. The company sends out maritime notices, so those are broadcast over the airways. AIS system, they're in that, and they have an onboard beacon, the light at the top, and they're really high profile, so they pop on radar. We've had no incidents with other boat contract in our time here on the Great Lakes. The company is shy of moving their drones into shallow depths and these heavy marine traffic areas. When it's no wind, they lose control. So there's certain things that they're reluctant to do. And when planning this 2024 survey, we had really good knowledge of what we could expect for travel distances based on prior deployments in the Great Lakes. So the questions we sought to answer operationally: can we rely on these drones? Can they cover the distances we need? And are they tough enough for the world that is Lake Superior? The biological questions we sought to address is: what is the abundance and the biomass of age 2 ciscos, and how does that compare to the age 0 estimate from the 2022 CSMI survey? Can 2 drones deployed for 84 nights in total provide acceptable precision at the lake-wide and at the jurisdictional scale, was a question. And finally, how does the precision of the lake-wide drone survey compare to our past crewed vessel CSMI surveys? During 2024, these are the tracks that the drones were accomplished. There were 2 drones deployed for 6 weeks. We set them out at the end of August and they were recovered in early October. They covered a total distance of 5,500 kilometers of transect. There's both day and night data here, and there's going to be a talk at the common session where Lars Rudstrom is going to dive into how we're using the daytime data to understand diel-vertical migrations of fish and mysids. So look for that talk tomorrow. We do pelagic fish surveys at night. The pelagic fish, where some of the species will be on the lake bed during the daytime. At night with DVM, they move up in the water column. Some of the species like Cisco school, those schools break down at night, so it's much easier for us to enumerate and characterize the size structure at night. The 2 drones here accomplished almost 2,100 kilometers of acoustics and 84 transects shown on the map to the right. And so we concluded based on this coverage in this 6-week window that yes, the sail drones were tough enough operationally for this task. We had opportunity towards the end of the sail drone mission to conduct a midwater trawl survey where we were trying to understand the species compositions in different bathymetric strata that we were studying. We collected 25 midwater trawls from the north shore, or from the south shore to the north shore. Ideally, we would have been able to collect more midwater trawl samples, but in 2024, we had a bit of a shortage of sailors at the Great Lakes Science Center. There's other high priority surveys that happen in the fall, so we got done what we could given the amount of sailors that we had. Some nice catches of Cisco and then Kai on the bottom there. By way of quickly describing our acoustic methods, we used it with the latest and greatest EchoView version 15. We set the minimum target size of interest at minus 55 decibels. We want to threshold out smaller backscattering things like mysids so they don't get included or bias our fish estimates high. Minus 55 decibels is equivalent to about a 5 centimeter fish or thereabouts. We process fish density data down to 100 meters. It turns out that the densities in Lake Superior at night below 100 meters are trivial, and it kept it consistent with the prior survey approach for processing. We actually used artificial intelligence for the bottom editing and the surface noise exclusion. It turned what would take months of labor-intensive post-processing into a weeks-long task. We set the elementary sampling distance. It's just the amount of travel distance that we're going to call a sample at 500 meters. And then we calculated in each of those cells, 10-meter high cells, the density estimate in each of those cells or layers in those 500-meter segments. We used the trawl catches to apportion the species. We didn't have enough trawl samples in the 2 shallowest depth strata to do anything with like water column depth, so all the samples were pooled to do the apportionment. At the 2 deeper strata, greater than 100 meters, we had enough trawl samples high in the water column and deeper to apportion above and below the thermocline. When we were calculating species biomass density, we used what we call the KISS method, or keep it simple, stupid. We just take the trawl proportions and multiplied it by the cell fish density, and then multiplied that species-specific density estimate for that cell times the average weight of that species from the trawl catches to estimate biomass density. I think the trawl catches are pretty informative, so we'll spend a little time on them. They're lake frequency distributions, so length is on the x-axis, count is on the y-axis. The 4 different bathymetric strata are shown with the shallowest depths at the top, the deepest waters at the bottom. The shallow zone catches were dominated by the 9-spine sticklebacks, shown in that blue color, and also rainbow smelt. And most of the fish in this particular strata were rather small-bodied. In the 3 deeper strata, we start to catch the Cisco, shown in green. They were not present in the shallowest depths, but they certainly were in all of the other depth strata we sampled. These fish that are about 20 centimeters in length, those are the age 2 Ciscos, and then you can see some bigger fish on the far right of the plot. Those are the adult Ciscos. At about 100 meters, there's a shift. The small-bodied fish in 30 to 100 meters are pink. That's rainbow smelt. And then at 100 meters, they're replaced with Kai, shown in the orange. So Kai and Cisco are predominant in the deepest waters of the lake. So I like to call this our big, beautiful map. It's how fish biomass was distributed. It's presenting here what's called NASC, or the nautical area scattering coefficient. Don't worry about that. That's a kind of a technical term, but what it really means is that NASC is proportional to biomass. The higher the NASC, the higher the fish biomass, and vice versa. And one of the things we can glean from this map is that there was high fish biomass throughout the entirety of Lake Superior. We can also see some hot spots, which are shown in the blue and green colors. These are very interesting. Some of them had density or biomass density estimates that were 12 times the mean. So very high density areas, no, 12 standard deviations above the mean, so incredibly high densities. If we had done less coverage, it increases the chance that these hot spots would have been missed, but because we have such great spatial coverage with the sail drones, we were able to capture these high hotspot zones. This is average density on the left, average biomass density on the right. Each panel is a different bathymetric strata, so the shallowest are at the top and the deepest strata are at the bottom. The colors coincide with different species, which are labeled on the x-axis. We sum all of the species to create those gray bars. It's the total fish density. In the upper left-hand panel is the density of fish in the 5 to 30 meter strata. So the highest density we observed was just shy of 1,500 fish per hectare. In the other three zones, the average density of fish was about 500 to 750 fish per hectare. This is like unheard of in Lake Superior and nothing I'd seen in my 25 years working on the lake. On the right-hand side is the same data, but biomass density is presented. Remember, we have high densities in the 5 to 30 meter strata, but because the fish are small-bodied there, the actual biomass levels is really low, less than 5 kilograms per hectare in that strata. The y-axes on the other panels are they differ from that first panel, and they go up to about 80 meters or 80 kilograms per hectare. And you can see the green there is the biomass levels of Cisco. It's almost 60 kilograms per hectare in each of those bathymetric strata. To put that in perspective, those estimates are comparable to the very high estimates in the 1990s in Lake Michigan, and a recent survey on Lake Huron, I think they estimated at about 8 kilograms per hectare, so those estimates are 7 times higher in Lake Superior than what we see in Lake Huron at present. Just incredible biomass of fish. So when we compared the 2024 estimates from the sail drone survey to the 22 estimates with a ship-based survey, we see a dramatic increase in abundance of Ciscos. And you're probably thinking, what the heck, Dan? That's not even possible because it's the same cohort of fish. You're absolutely right. This is not something that happened biological, but it has something to do with our survey methodology. In that year, we learned that the ship-based surveys miss a lot of fish in the very upper water column. And we know that because we deployed what's called an autonomous underwater vehicle that had both up-looking and side-looking acoustic channels. So we were able to calculate what proportion of small-bodied fish or age 0 in the left-hand panel were present in the top 5 meters versus the entire water column. And we did the same thing for larger targets or yearling and older targets. So it turns out about 55% of the age 0s were present in the top 5 meters where we could not effectively sample them with a ship sounder. That's because the transducer has to be some depth into the water. It takes some distance for that transducer wave to fully form. And also the volume of water that we sample really close to the transducer is quite small. That's not true for the yearling and older fish. On the far right-hand bottom there, only about 4% of this targets of that size were present in the upper water column. They tend to be more associated with the thermocline and deeper water where they're more available to the acoustic sampler. It's a lot of fish, almost 5 billion fish in Lake Superior Ciscos at present. So how do the lake-wide CVs compare? Because we collected so much data with the sail drone echo sounders, we were able to sample that data with replacement to understand how on a lake-wide scale the prey fish biomass CV, or the coefficient of variation, would vary with sampling distance. We've got some vertical lines here. The red is our model prediction of what we accomplished with a ship-based survey at the 56 CSMI sites at about, 250 kilometers of effort thereabout. That has a CV of 13%, which is good. When we manage fish populations, I think we should be trying to get CVs that are at least 25% or lower. So that has a good CV, and that's not a surprise because we had a prior lake-wide survey that we were able to utilize to understand what level of effort we would need to do a good job with that CSMI survey. But look at how well we did with the USV, that's the sail drone, the realized survey, almost 2,000 kilometers. The CV on that survey is about 5%, which is just freaking phenomenal. Sorry. And then we also we modeled what that CV would have been if we had only done half of the sail drone effort. That's the blue dashed lines, and if we had doubled the sail drone effort with the far line on the right. But the bottom line here is this lake-wide survey with these USVs had remarkable precision. We can have a high deal of confidence in the biomass estimates that we derive from it. How do they look on the jurisdictional level? Here it's the same sort of thought behind the plots, but we have the jurisdictions in columns and the depth layers in rows, okay? And the blue lines are how much sampling was covered by the sail drone in each of these combinations of jurisdictions and depth zones. The dashed lines are the estimated CV in that combination. And one of the things we can see is that the less than 30 meter stratum at the top is that some of these CVs were not really great. Like in Michigan waters, it was 32% or thereabouts. It was better in Ontario and Wisconsin. In Minnesota, we weren't able to get the drones into shallow water. It's really steep shoreline there, so they didn't feel comfortable taking them there. But I think we could improve the estimates in this shallow depth by possibly adding small vessels carrying echo sounders that could, pick up acoustic data in that zone. The estimates in the 30 to 100 meter, and that's the second row down, all had really great precision in all of the jurisdictions. In the 100 to 200 meter stratum, I think we could have done more sampling in Wisconsin waters. We sort of undersampled there, so its CV is about 22%. And offshore, in the really deepest waters, greater than 200 meters, all of these different jurisdictions had wonderful precision, except in Wisconsin, where there's no water greater than 200 meters available to sample. So I'm winding up here. To take home messages as I see them, I think that the USVs can cover the whole lake at a cost of about $400,000. That's the cost to ship them, unpack them, assemble them, use a crane to lower them in the drink, tow them out for calibration so that we know the transducers on the echo sounders are working properly, conducting the surveys, and then repeating that whole process at the end of the survey. I think these less than 30 meter depths are always going to be a challenge for these USVs to sample because they're afraid that their $500,000 unit is going to get damaged. So I think it's really important that we think about using small vessels to survey these depths in the future. We have developed some wonderful AI routines that leads for the automation of this labor-intensive post-processing steps and R code for the density calculations and the artwork we shared today. I think that these USVs can ease the burden on large crew vessels by assuming the acoustic data collection role. That is my dream. The jurisdictional level estimates are really possible. We demonstrated that. And we can build, I think, an even better mousetrap or a better survey next time by taking what we learned in this survey and making sure that we're covering some of those combinations of jurisdiction and depth strata better to improve the CVs there. And finally, I think acoustic data still needs biological data to apportion the species. So if we can use these drones to do the bulk of the acoustic lift, what would give us more ship time to collect more trawl samples and help with the apportionment part of the problem. And with that, I thank you for your attention, and I will gladly answer questions.